Okay, so I'm doing problem number 17 from chapter 4. So we can start by drawing the sketch for the problem out. So we have two spherical shells, one with a radius of 0.50 meters and the other with a radius of 0.51 meters. So first we'll use Gauss's law to figure out the electric field in this region between the 0.50 meter spherical shell and the 0.51 meter spherical shell. So if we draw in our 0.5 meter spherical shell and consider a Gaussian surface around it, and we'll say that it's a sphere with a radius of r. Next we can apply Gauss's law, which says E dA is equal to the charge over epsilon naught. Now, since we considered a sphere, the electric field is going to be constant at all points, so we can pull that out of the integration. And then the surface area of this Gaussian sphere is just 4 pi r squared. We'll assume the inner plate to have a charge of q, and so we'll leave that as q and we'll leave the right side as epsilon naught. So we get that the electric field is equal to q over 4 pi epsilon naught r squared. Now 4 pi epsilon naught, that's just 1 over k, right? But it's in the denominator, so it goes up and becomes kq over r squared. Next we need to find the voltage between these two surfaces. So we can do that by using the formula V equals the negative the integral of E dot ds. So we have negative integral of kq over r squared. Since instead of s we're using r over here, we'll use that here, dr. The kq comes out and we have this integral. So we can take our limits to go from 0.50 meters to 0.51 meters. And if we find this integral, we get negative kq, and this term inside simplifies to negative 1 over r. And next we just plug these numbers in and we see that the voltage difference is equal to kq over 0.51 meters minus kq over 0.50 meters. Next we can go into our formula for capacitance, which says that capacitance is equal to charge over delta V, and then we can use an absolute value sign over here since we don't know if this V we calculated over here is going to be positive or negative, since we just assumed that the inner plate is positive, but it could be either way. So we have q over kq over, so I'm just substituting delta V for this expression, so we can factor a kq out, so we have 1 over 0.51 minus 1 over 0.50 meters. The q's cancel out, and this simplifies to give us a capacitance of around 2.93 times 10 to the negative 9 farads if we plug everything in correctly. Part B asks us to find the energy stored in this capacitor if we have a potential difference of 100 volts. So to do that, we can start off with the formula E equals 1/2 Q delta V. Now since we weren't given Q directly, we can solve for Q using the equation C equals Q delta V, and then that gives us Q equals C delta V. We'll take this expression over here and put it back into our first expression, so we have 1/2 C delta V times delta V is equal to our energy, which simplifies to 1/2 C delta V squared. If you plug in your capacitance as 2.83 times 10 to the negative 9 farads, and our voltage is 100 volts, we find that the energy stored is equal to 1.4 times 10 to the negative 5 joules, or 14 microjoules.